Hey everyone, so as you can tell, I'm suddenly doing vectors and I'm not doing an introduction, but instead talking about directional cosine. Now the idea is that it's currently September 2021 and I'm not going to do any more vectors content videos nor complex numbers content videos until this year's A-level end. Reason being that I don't want to do a double chop for the current A-level batch. Instead, I'll move on to stats afterwards. And the idea is that, well, I've already done a vectors crash course and uploaded the recording to this channel. And for the complex numbers lectures, well, it's held at Inky Learning's channel, so do check out Inky Learning and the recordings for the crash course for complex numbers. It's rather is a two-part lecture. But coming back to vectors, I kind of missed out a particular concept, and this concept is called the directional cosine. Right? So the idea is that if we have a line L, all right, and I'm going to write out the equation later on. If this line L would make three angles with the axis, all right, you have alpha, usually given to the angle between x-axis and L, beta, y-axis and L, and lastly gamma, well, we know what's left, z-axis and L. And what happens is, if we were to actually really write down what is going on here, so we know that x-axis and L has the angle of alpha, so in order to kind of relate it, we use the dot product, where we have the direction vector of L. Let's say we have the direction vector as A plus, we'll write it on top here, lambda DEF. So we have DEF, the direction vector of L, dotting x-axis, which has direction vector 1, 0, 0, over the modulus of DEF, simply D squared plus E squared plus F squared. And then, well, mod of 1, 0, 0 is simply 1. And this will give us cosine alpha. Do that for the rest and you get the following. Alright, so I'm going to skip ahead. D over, or rather D equals, so I'm going to write it this way down, and then I'm going to make a proof from here. And you notice that if we do this for the other two angles, we're going to get E equals to root D squared plus E squared plus F squared cosine beta. Then F equals to root, again, D squared plus E squared plus F squared cosine gamma. And what do you notice about our direction vector? Notice that our direction vector, DF, is simply root D squared plus E squared plus F squared bracket cosine alpha cosine beta cosine gamma, and this results to our direction vector of this particular line L to have direction vector cosine alpha cosine beta and cosine gamma. So this is the mathematical way of seeing it, the mathematical proof. Another way of seeing it is that if this line makes an angle with an x-axis, it's basically moving the x coordinates is changing at respect to the x-axis at this particular angle. Alright, so let's say this x value is moving across to that, is moving at, let's say, 60 degrees. Same thing if it's like this is the y-axis, then the y value is moving at a particular angle, and same thing is applied to z. That is why your direction vector is cosine alpha, cosine beta, cosine gamma, where the cosine comes from your dot product. And what else do you notice? Okay, I'm going to do something really fun here. So I'm going to draw a line across so that we can focus on the top and at the bottom. Now, if we notice, right, I'm going to rewrite it a bit. So we're going to get D squared equals to D squared plus E squared plus F squared equals to cosine squared alpha. All right, and we do that for the rest. We're going to get E squared equals to cosine squared beta over D squared plus E squared plus F squared, and same thing for our F. We're going to get F squared over D squared plus E squared plus F squared equals to cosine squared gamma. Add these together, what do you notice? So we get cosine squared alpha plus cosine squared beta plus cosine squared gamma equals to, on top, D squared over D squared plus E squared plus F squared. You notice that all of them has the same denominator, and on top is D squared plus E squared plus F squared. And you notice that, hey, we basically get the same denominator and numerator, which then equals to 1. This then brings us to our next identity, where we have cosine squared alpha plus cosine squared beta plus cosine squared gamma, giving us 1. Alright, so these are the proof for our directional cosine. So let me just conclude this portion of our vectors, which I've kind of forgotten about to go through in our crash course. So if we have L making an angle of alpha and beta and gamma with the three different axes, so x, y, z axis, the direction vector is cosine alpha, cosine beta, cosine gamma. Alright, and we know the identity is cosine square alpha, plus cosine square beta plus cosine square gamma would give us a value of 1. And this is actually an important identity because sometimes they will give us two of the angles, and then we need to find the third angle and then be able to find the direction vector of the line. Alright, so there we have it, the directional cosines, where alpha, beta, and gamma are the angles made between the line and the x, y, z axis respectively. Alright, so there we have it, the directional cosines.